All right, well, hello everyone, and welcome to the first of our videos on the Chapter 8 material, where we're going to start looking at the additions across a carbon-carbon double bond. We just finished up talking a lot about substitution reactions, and in particular elimination reactions, where we can form carbon-carbon double bonds. And now we're going to look at the reverse of that process, where we can add the elements of some molecule across a carbon-carbon double bond. And again, the idea here is to continue with our theme about sort of interconverting functional groups and learning some more of the organic reactions that we have available to us. And so here's kind of a general representation of an addition reaction. We've got a carbon-carbon double bond. We've got two elements that are participating in a molecule of some kind here, X and Y represented in general, and they're adding themselves across that carbon-carbon double bond. And we'll look at some specifics of these reactions in some detail. I will add one brief note here at this point, and just to say that these may be the same. That is, we'll see, for example, that they could be two atoms of the halogen, so bromide chloride, for example, or even two atoms of hydrogen in a reaction that we've actually seen earlier in the course where we add hydrogen across a double bond in hydrogenation reactions. But we'll also see a number of examples where these are not the same as well. So here, for example, we can have a table of these reactions and different types of these addition reactions, and we'll kind of work through them more or less sequentially like they are in this table, where we look at adding HCl or HBr across a double bond, or hydration where we're adding a molecule of water to that double bond, or hydrogenation again as we've touched on, or halogenation again we've referenced just briefly here, and we'll see some more at the end, and a little bit of halohydrin or dihydroxylation perhaps at the end if we have some time to kind of finish this up at the end. So let's take a look in some more detail about this addition reaction and kind of imagine what we would expect to observe about this mechanism that we would see here, well, how these addition reactions would behave. Again, that carbon-carbon double bond, we spent some time at the beginning of the course giving what we think is a good model for that, where we think of it as a pair of electrons between two carbon atoms in a pi orbital, or in that sort of molecular orbital, the bonding molecular orbital. And so there's a lot of electron density that's associated with those carbon-carbon double bonds. And if we imagine an electrophile of some kind being present, then we can imagine those two electrons in that carbon-carbon double bond acting roughly like we would expect a nucleophile to act, where they are attacking some kind of an electrophile. And so let's imagine what that process would look like here, and I'll put this in equilibrium, and we'll talk again a little bit more later, and we've already got a good idea about how we'd assess whether these would be in equilibrium or not. But again, where we would imagine that electrophile adding across that carbon-carbon double bond, and the key thing, of course, is that it would leave behind a full formal positive charge. And we've just spent a lot of time in Chapter 7 talking about carbocations, their relative stability, and the kinds of things they can do. So we'll see quite a bit of that material again here as we kind of talk about these mechanisms for eliminations. And then we could imagine here a nucleophile, and I'll put a negative charge on the nucleophile, but of course we know that there are nucleophiles that don't necessarily have to carry a negative charge. We'll see some examples of those here. We can imagine that nucleophile now attacking that positive charge, that carbocation that's left behind, leading us to a product that looks a bit like we talked about a minute ago in general. We get something that looks like that. So an electrophile and nucleophile neutralizing the negative charge on the nucleophile, adding across that double bond. So now again, as I've drawn it out as a stepwise reaction, we'll see a couple of examples that do take place stepwise, but they may not necessarily involve a full formal positive charge on the carbon atom. We'll see a slightly different reactive intermediate, but in general, the ideas that we're discussing here are things that can apply quite well to our analysis of these addition reactions. So maybe a specific example of this, we can imagine, for example, a double bond and having it in the presence of a very, very, very strong acid like HBr. So hydrobromic acid, instead of hydrochloric acid, hydrobromic acid, again, an exceptionally strong acid, a pK of about -9 or so. And we can imagine that the two electrons in that double bond attacking the proton on that HBr and kicking the electrons onto the bromine atom itself. I'll draw this as an equilibrium process, and we'll talk a little bit later about whether we would predict that to be in equilibrium or not, but we've seen the reverse of this process anyway, so we know that the forward and reverse reaction can occur here. Leaves a formal positive charge, and then we draw that Br minus that can act as an electrophile or nucleophile, excuse me, and come in and attack that full formal positive charge, leading to the kind of product that we would predict to observe here. Again, really, this is the opposite of that so-called E1 mechanism that we spent some time talking about in Chapter 7. So we can get the reverse process going, and we'll spend most of our time in Chapter 8 talking about what kinds of these addition reactions we can get to observe. Well, let's look at another aspect of these reactions I want to focus on here for a minute. And again, we'll just get this reaction on its own without all the clutter of the mechanism and just take a look at what we expect to observe here. And in particular, what I want to look at is what would we expect to observe when we take into account the thermodynamics of what's happening in this particular reaction. And so overall, what we observe for this reaction as written, the addition of HBr across a carbon-carbon double bond. Again, if we look at our bond enthalpies, overall all bond enthalpies for this reaction as written are negative. This is an exothermic process. It releases energy. Of course, HBr and the carbon, bromine, and carbon hydrogen bonds are bond energies we can look up in table 6.1. The carbon-carbon double bond energy isn't in table 6.1, but we can give that to you, or it's provided in the textbook. And this section of the textbook's got a really nice description of the bond energies and does some of the calculations for us. So in general, these reactions overall proceed with a negative bond enthalpy. But if we look at this time the changes in entropy, now we said earlier for some of the reactions that we could look at, we could ignore for the most part entropy because the entropy changes were negligible. But that's not the case here anymore. We've got 2 molecules of substrate going to 1 molecule of product. So overall, these addition reactions also have a negative entropy that we're observing for them as well. And so that makes our overall thermodynamic considerations a little bit different than what we've seen before. So if we look at delta G, of course, is the addition of delta H minus T delta S. What we observe here, of course, that temperature term has an influence on what's going on. Of course, a negative delta S times a negative temperature is an overall positive term. So here, the consideration that we get is if we look at low temperature, for example, if temperature is low, then that enthalpy term dominates, and delta G will overall be negative if the enthalpy term dominates at low temperature. And if a negative delta G means that this reaction is overall spontaneous. So at low temperatures, we'd expect these to be spontaneous. But then if we do the reaction at high temperature, and that entropy term dominates, if the product of delta S times the temperature becomes larger than delta H, what we observe is that the overall energy becomes positive. That is, this reaction does not become spontaneous at a high temperature. We'd expect the reactants to dominate at a high temperature. So all of that thermodynamic consideration has a practical implication for the way we do these kinds of reactions. So in general, we see that addition reactions, we do them at low temperature. Those addition reactions we do at low temperature, and that's a direct consequence of the thermodynamic considerations, and in particular that entropy term. And so this, although it seems again like a small piece of chemical trivia, will have a big influence on how, by the time we get to the end of the chapter, we pick the conditions that we want to run a particular addition reaction under in order to be able to make sure that we get the desired product. And so for now, I'll leave it there, and then in the next video, we'll start looking at some more specific addition reactions and how to what kinds of products we predict out of them.